exists the possibility of faster-than-light communication through the use of quantum entanglement. The universe is so enormous that it hurts. Interstellar communication is a difficult obstacle that will need to be overcome by advanced civilizations, in the event that they eventually expand across the star's Earth in empires that span the entire galaxy. In a frustrating turn of events, Einstein explains that particles cannot be accelerated beyond the speed of light, since doing so would demand an unlimited amount of energy. This would result in a speed restriction being placed on communication. The speed of light may appear to us to be incredibly quick, but when viewed from the perspective of the cosmos, it is quite sluggish. This is so slow that the communication lag periods for an empire that spans the entire galaxy may be as long as 100,000 years. Just take a moment to consider the massive changes that have occurred to our own species over such a long period of time. To put it into perspective, our ancestors had not even left the African continent at that point, let alone invented agriculture, writing, or science. Take into consideration the innumerable wars, revolutions, periods of expansion and collapse, epidemics, famines, and socio-political transformations that have occurred over that time period. It might appear to be a fantastical idea to properly sustain a coherent galactic empire when communication lag times significantly exceed the estimated timeline of civilization itself. This is certainly the case when viewed through the lens of human standards. It is obvious that communication that is faster than light, sometimes known as FTL, could come to the aid in this situation, particularly if it were answered, which means that it would be immediate. Even if ships and objects are physically constrained to move slower than the speed of light, the ability to communicate faster than light would be a game changer for such empires. This technology would also benefit more primitive civilizations like our own, as it would reduce the amount of time that it takes for communication to take place across the globe, between our spacecraft, and possibly even between Earth and our outposts in the distant solar system. Unfortunately, according to the theory of relativity, the speed of light is not simply the speed of a photon. Rather, it symbolizes the speed of causality in its purest form. Due to the fact that under relativity, it is impossible to reach a consensus over the meaning of a simultaneous moment. In contrast to Newtonian physics, which adopted the idea that there is a universally accepted absolute sense of time across the universe, Einstein demolished this notion and demonstrated that it is dependent on the relative frame of reference of the observer. Therefore, breaking the speed of light is not simply a matter of not having sufficient energy. Rather, it has the potential to fundamentally violate causality itself. For instance, it would allow one to receive messages before they were ever transmitted. It is recommended that you see the film that we created earlier on the subject of FTL causality violations if you are interested in gaining a more in-depth understanding of how these paradoxes come about. In accordance with the causality protection conjecture, which was famously proposed by Stephen Hawking, these kinds of grandfather paradoxes are widely rejected since they undermine the logical underpinning of physics. However, that statement of impossibility really just derives from the theory of relativity, and the majority of physicists, including Einstein, would agree that any physical theory is really just an approximation to reality and is not a literal description of it. This would seem to be pretty bad news for our hopes of fast-traveling light, FTL communication. So if we temporarily throw relativity out of the window, which remember is our best explanation of the universe at the greatest of sizes that left us with quantum physics, which is our best description of the cosmos at the smallest of scales, it is possible that many of us may place greater faith in the predictions of quantum physics than we will in those of relativity, despite the fact that his weirdness cannot be denied. It is important to remember that this is a theory that is utilized in a much more practical manner in everyday life, such as within the semiconductors of your phone or computer. In addition to this, its predictions have been tested with an unbelievable level of precision. In the case of the electron, for instance, the anomalous magnetic dipole moment has been measured to 1 part in 100 billion, and it continues to be in perfect agreement with the forecast that was made based on theory. The physicist Roman Jacu is quoted as saying that quantum mechanics is an absurdly effective process. Quantum mechanics is appealing for a number of reasons, one of which is because it was developed without the influence of relativity. Although it is possible to combine the concepts of relativity and quantum mechanics in order to get anything resembling quantum field theory, the essential principles are not based on the foundation of relativity. When one takes quantum mechanics and looks at it in a rather basic manner, it appears like there is a method to achieve FDR communication, and that means is quantum entanglement. This is even more wonderful news than the last one. Following our earlier video in which we explained why FDR violates causality, several of you commented on quantum entanglement as a possible workaround. Since this is something that many of you have mentioned, let's discuss it today. The idea of a quantum entanglement communicator, or QEC for short, has been widely discussed in the realm of science fiction for a considerable amount of time. For instance, the Three-Body Issue series is a good example of a system that is used in books. In movies, you have the concept of avatar, and in video games, you also have the concept of Mass Effect. In light of this, let us explain why so many fictional renderings have chosen this as their potential FTL communication method, as well as what our current understanding of physics has to say about the possibility of a QEC device being a reality. Those who advocate for quantum entanglement emphasize the fact that it has been demonstrated beyond a reasonable doubt that the effects of entanglement travel at a pace that is greater than the speed of light. On the other hand, that statement by itself is not precisely the same as declaring that thus FTL communication is permitted. Nonetheless, naively, it appears as though it should indeed make it conceivable. What exactly is the concept of quantum entanglement? First, let's take a look at a quantum superposition, which is one of the fundamental aspects of quantum theory. Just to get things started, let's envision a single particle that is completely apart from all the others. Let us take into consideration a certain quantized attribute of that particle, which we will refer to as spin. Spin can be either up or down until something interacts with the particle, which could be an observer making a measurement, for example. In contrast to what one might anticipate from a classical perspective, the quantum state of the particle spin is not either up or down. Rather, it is a superposition of the two available states. When described in this manner, the particle is almost entirely composed of an equal mixture of the two. It is possible that this superposition state will collapse into a single state if we proceed with the measurement of the particle's spin. In this particular scenario, the likelihood of each event is 50%. The concept that the cosmos is inherently probabilistic is something that many people find unsettling when they first come upon it. Quantum physics compels us to accept this viewpoint. Now it is essential to emphasize that prior to this collapse, it is not simply the case that we do not know the spin of the particle at 50-50 odds. Rather, it actually lives in a kind of ghost-like overlap of the two that is 50-50. The classic thought experiment of a cat that is locked in a box and ends up being both dead and alive at the same time was made by Erwin Schrödinger, who was one of the builders of quantum theory. Schrödinger's thought experiment is credited with illustrating an extreme consequence of this. As a matter of fact, entanglement is nothing more than a particular instance of a superposition, and it is a superposition that involves two or more particles. However, rather than being a general superposition, it is a superposition of correlated measurement outcomes. This means that the measurement of one particle is coupled with a specific measurement outcome for the other particle. The most common example of this is spin, which occurs when two particles are produced together in such a way that the sum of their spins is zero. Although we are able to entangle a wide variety of various attributes of particles, spin is the most common example. It is still a superposition, and as a result, neither of the particles actually possesses a definite spin value. However, due to the fact that the sum is zero, when one of the particles interacts with the outside world and selects a particular spin, for example, up the other particle, reacts by collapsing to the opposite spin state, which in this case is down. Even if we take these particles and separate them over large distances, this phenomenon appears to take place in a moment, which is one of the most extraordinary aspects of the phenomenon. As soon as the spin state of one of these particles is collapsed, the spin state of the other particle also collapses. However, it is more true to say that measuring the spin state of one of these particles collapses the state of the pair. This is due to the fact that when it comes to entanglement, the particles are in this together. He referred to this phenomenon as spooky action at a distance. And it caused Einstein a great deal of concern because it appeared to be in contradiction with his theory. In fact, he collaborated with his colleagues Podolsky and Rosen, And the three of them prepared a paper in which they asserted that quantum theory must be incomplete as a consequence of this. This work is commonly referred to as the EPR conundrum, which is derived from their initials. On the other hand, we now know that this astonishing result of quantum theory appears to be robust, and the speed at which this activity takes place at a distance has even been measured to be at least 10,000 times faster than the speed of light. It is commonly envisioned that a QEC device will be able to take advantage of this particular aspect of quantum mechanics. The fact that activity can take place at a distance in an instant is without a doubt evidence that full-time travel, FTL, communication is feasible, right? It is true that the devil is in the details, as it usually is, for the reason that you intend to use this for communication. What exactly is it that you intend to do? Consider the following scenario. We have two particles that are entangled in such a way that their total spin is equal to 0. We load one of these particles onto a spaceship that we are going to refer to as Bob and send it to an extrasolar planet. Meanwhile, we leave the second particle behind on Earth in a control center that we will refer to as Alice. The idea is that once the spacecraft has completed its investigation of the exoplanet, it will use this entangled pair to inform us whether Bob believes the planet is habitable or not. This will save us from having to wait for a signal traveling at the speed of light to reach us, which may take a significant amount of time. Therefore, here is the question. The question is, what exactly is Bob meant to do in order to communicate to Alice that he has been successful? In light of the fact that the only thing we are ever capable of doing with particles of this kind is to open the box and interact with them, which will result in the collapse of their wave function and their uncertainty. If Bob does that, then the particle will collapse and decide to be a spin instead of a free particle. You may expect that spin to be up 50% of the time, and 50% of the time it will be down. Most importantly, Bob does not have any say or influence whatsoever in that matter. As was said before, quantum theory asserts that the universe is inherently characterized by a high degree of probability. This indicates that when Alice examines their particle at the anticipated time, it will either be higher or lower, with the probability being equally split in either direction. At this point, Alice does not have any way of knowing that Bob's particle is in the opposite state of Alice's particle, at least not yet. This is despite the fact that it is true. It is possible for Bob to send a standard radio signal that indicates the spin that it observed. However, this would be considered communication at light speed. As a result of the fact that Bob is unable to coerce an entangled particle into adopting a specific spin, there is no way that this concept may really be utilized to carry any information. Probably at this moment, your mind is racing, attempting to come up with a solution that would allow you to go around the problem, and you are not the only one doing so. Over the years, a great number of physicists have attempted it. Bob could take their particle and just continue measuring the spin state again and over again until they got the result they want, which would force Alice's particle into the opposite of that desired condition. This is a straightforward idea that could be implemented. The entanglement, on the other hand, is lost the instant that either particle's spin state is measured. Thus, unfortunately, this too does not work. It is similar to a one-time deal in that it does not continue beyond that. The depiction in Mass Effect 2 appears to give the impression that the entanglement of a single pair continues even after the entanglement state has been measured, which is not the case. This is one of the faults with the depiction. Okay, that's all right. It's possible that you'll try to get around this problem by employing a large number of particles rather than just one. Suppose, for the sake of this discussion, that Bob is interested in achieving a spin-up. To get the desired outcome, they begin by opening the first particle, and if it is not in a spin-up condition, they proceed to continue doing so until they achieve the desired outcome. Let's pretend that after a total of 5 attempts, Bob is finally successful in achieving a spin-up result. Take into consideration once more what Alice sees. Because they are unaware that Bob stopped at 5, they will continue to read off a series of random spins because they have no understanding what happened. In addition, this assertion is correct, regardless of whether Alice or Bob is the one who opens the package first in each case. Alice is not given a message, but rather a stream of random integers. Now that we've reached this point, it's possible that some of you have not yet given up and are beginning to think in a more sneaky manner about this situation, mainly due to the fact that there is undoubtedly a method by which we may utilize this for FDR communication, right? To be honest, whenever we have a conversation about this topic, there is always someone who suggests the following possibility. There is a possibility that we do not give much thought to the real spin state of the particles. With some reluctance, we acknowledge that the result will invariably be a random one. In its place, we use a 1 to indicate a state that is entangled and a 0 to indicate any other state. Alice is doing an experiment that is similar to a double-slit experiment, and the typical scenario that is offered for this scenario is that a number of particles are entangled with one another. In this particular scenario, the answer normally indicates that Alice should observe an interference pattern while the particles are entangled. However, as Bob measures his collection of particles, the wave function collapses and Alice will instead begin to observe 2 bright spots above each hole. In the event that we are being technical, double-slit experiments are concerned with locations rather than spins. Nonetheless, we may perform an experiment that is comparable to a Rabi oscillation experiment in order to investigate spins. However, this is not really the point at all. The most important thing to take away from all of this is that Bob has the ability to decide whether or not to make their measurement, and as a result, the instantaneous reaction that Alice witnessed would be considered FDR communication. A fundamental flaw in this proposition is that it is based on an incorrect premise. In the event when 2 entangled particles are separated and only one of them is forced through an experiment that is similar to a double slit, the experiment will not produce another interference pattern. Therefore, regardless of whether the 2 individuals continue to be entangled or not, Alice will always observe that there is no interference, and as a result, there has been no communication that has taken place. Yes, it is possible to achieve interference. However, in order to do so, you would need to force both of the entangled particles through the double slits rather than simply one of them. First, we need to have a better understanding of an interference experiment so that we can see why this wouldn't work. When conducting an interference experiment with the purpose of determining the superposition state of a single particle, the first step is to apply an operation that allows for the controllable variation of the relative phase between the 2 components of the superposition that are supposed to be present. An illustration of this would be the utilization of a magnetic field in the event that the superposition is between 2 spin states. Next, an operation is carried out in order to rejoin the 2 routes. And in this case, a magnetic field is applied in the direction that is perpendicular to the direction of the pass. Last but not least, one now determines whether or not the particle is in a particular condition, such as spin-up after the roots have been joined together. The oscillatory reliance of this probability on the imparted phase is what identifies the superposition as being present. In the event that the superposition is in the joint state of the 2 particles, which is the situation for an entangled pair, then the operation that we need to do in order to combine the 2 paths prior to carrying out a measurement must be a joint action of those 2 particles. In other words, in order to determine whether or not the 2 particles are in a combined superposition state, we need to make it possible for them to interact with one another within the interference apparatus. Either we will have to bring the particles back together, or we will have to use a force that has a long range, such as the Coulomb force, which, as we all know, cannot travel faster than the speed of light. When all is said and done, this indicates that Bob is unable to send information to Alice by measuring or not measuring their particle. This is the conclusion that can be drawn from this. We simply need to find some way, any way, that Bob may alter the state of their particle, and then the entanglement would enable the information to be transferred in a time-traveling manner. Now, some of you might still be stubbornly holding to optimism in this situation. After all, we just need to find a way. Let's give one more concept a shot, one that is a little bit more sophisticated than the others. You should keep in mind that prior to measurement, the spin of a single particle exists in a state that can be described as superposition. In reality, however, the spin is not simply positive or negative. Rather, it is pointing in a space-based vector that is unknown. In point of fact, it could be in any which direction. On the other hand, when we measure it along a certain axis, let's say the y-axis, we place the particle in a position where it must choose between being up or down along that axis. On the other hand, we could additionally opt to measure it along the x-axis instead, which would compel the particle to be either in an upward or downward direction along that axis. From this point forward, let's refer to those states as right and left, because the axis is represented horizontally here. Taking all of this into consideration, it is likely that some of you can see where we are going with our potential QEC gadget here. If Alice and Bob notice their particles spinning in an X sense, which means that they are spinning left and right, then they have already come to an agreement that this is equivalent to a 0. On the other hand, if they see that their particles are spinning in a Y sense that is in an upward and downward direction, then this is equivalent to a 1. Bob is now in a position to decide whether he will measure the spin along the X-axis or the Y-axis. It is up to this spacecraft to decide what to do then. In the event that Bob selects X and measures, for example, a left state, then Alice's particle will immediately collapse into a right state. On the other hand, if Bob selects Y and subsequently measures, for example, an up state, then Alice's particle will collapse into a down state. The one that Bob is sending is that it is unfortunate that this configuration does not work either. And the more intricately complicated we create these schemes, the more detailed the response will eventually become regarding the reasons why they do not function. In this particular instance, the answer is going to be determined by what Alice perceives to be the two possible outcomes. Due to the fact that Alice is unable to determine whether Bob selected X or Y in advance, she is required to use a single system of measurement as the default configuration. First, let's take a look at the most straightforward example, which involves Bob taking a measurement in the same direction that Alice has decided to take the measurement in. When it comes to this particular illustration, let's focus on the Y-axis. This indicates that Bob measures in Y and that he will receive an up 50% of the time and a down 50% of the time with his measurements. Given that Alice is also measuring in a Y sense, it is reasonable to assume that they will observe the opposite of whatever Bob obtains. Therefore, this indicates that 50% of the time will be spent down and 50% of the time will be spent up. Up to this point, this has not shown to be very helpful. Alice is still receiving a random sequence exactly like she did before. Let us now take into consideration the alternative case in which Bob decides to measure in the X direction rather than the Y direction. Now, Bob will randomly measure a left half of the time, and equally as often he will measure a right half of the time. This indicates that Alice's particle must collapse into either a left or right state in order to be functional. Keep in mind, however, that Alice does not have any way of knowing in advance that they ought to be performing a measurement based on X measurements. Instead, they are only adhering to the practice of making measurements based on the Y-axis in our case. The question now is, what exactly does Alice come to notice? To put it another way, this left and right spinning particle is essentially compelled to choose between spinning up or spinning down. The condition is somewhat analogous to a coin that is flipped over on its side. It is Bob who is responsible for driving the particle into an X-basis sense throughout the measurement process, which ultimately results in the collapse of the wave function. Within the context of this comparison, however, Alice can be interpreted as exerting a force comparable to gravity on the coin, thereby compelling it to settle into either a heads-up or heads-down condition on its own accord. There is a random probability of 50% that one will emerge. The following is the outcome that we are left with after all of this has transpired. In the event that Bob measures in a Y sense, Alice, who, as you may recall, also measures in a Y sense, will be able to see up or down to at least 50% probability. If, on the other hand, Bob decides to convert to an X-sense measurement, then Alice, who is still using Y, will perceive the likelihood ranging from up to down to 50%. In other words, it does not matter what Bob does to Alice, because she will still receive the same thing. Whatever the case may be, Alice is left with a sequence that is completely random, exactly like we had before. In spite of everything that has been done, including all of these suggestions, methods, and workarounds, we are essentially back where we started. Due to the fact that Alice and Bob still do not have a means of communication that is FTL at the end of the day. A random sequence of zeros and ones is all that their QEC device accomplishes, at least from their point of view. This is the only thing it could possibly do. The situation is really not that dissimilar to a cosmic devil slicing a pair of shoes into two parts, giving one of them to Alice and sending the other shoe to Bob in a hidden shoebox. In a practical sense, the situation is virtually identical. Before Bob opens their box, there is a 50-50 chance that the shoe will be on the left or the right. When Bob opens their box and discovers a shoe that is designed for left-footed people, they are able to deduce that Alice must be wearing a shoe that is designed for right-footed people. However, doing so is not communication. There is no way that Bob could possibly use the shoebox to communicate with Alice in any manner, shape, or form. Other than the ones that are discussed in this video, there have been a great number of alternative schemes that have been offered. However, none of them have ever been successful in building an FTL system. In point of fact, physicists have gone even farther and demonstrated that if the fundamental assumptions of quantum mechanics are assumed to be valid, then it is possible to demonstrate in a formal manner that such communication is impossible. This theorem is known as the no communication theorem when it is applied. In the end, it all comes down to the reality that, to the best of our knowledge, it is not possible to exert any control over the state into which a wave function would collapse. There is a sense that the universe is inherently random, like a god rolling dice. Consequently, as a consequence of this, Alice and Bob are destined to never witness anything other than random sequences. In spite of this, quantum entanglement continues to be a fascinating and extremely valuable concept, serving as the basis for quantum cryptography and quantum computing. It has the potential to become an increasingly prevalent component of our contemporary technology over the course of the next few decades. In addition, with regard to fast-forward travel, it is true that activity at a distance travels at a speed that is greater than the speed of light. Consequently, does the fact that Einstein's speed limit is incorrect, that his limit is not some type of fundamental law of nature, demonstrate that Einstein's speed limit is incorrect? If that is the case, don't you think it would at least give us some hope? The door would be open to the possibility of another FTL option in the future, which would be a positive development. On the other hand, even that is not accurate, for the simple reason that Einstein's speed limit is not truly about the speed of light. Do you remember, the issue at hand is one of causality? In reality, relativity is very comfortable with the idea that things can travel faster than the speed of light. The problem is that information is incapable of doing that. As an illustration, consider the process of moving a laser spot from point A to point B across a distant plane. You have the ability to have that spot travel across the plane at a speed that is faster than the speed of light. However, A cannot potentially utilize this to send a message to B at speeds that are superluminal. When we consider the concept of causality, we realize that actions that take place at a distance do not constitute a violation. In spite of the fact that it is not local, it is not non-causal. The fact that quantum physics are conceptualized from completely distinct starting points in order to describe dramatically different scales is what makes this realization so peculiar. To reiterate what I stated previously, the standard version of quantum mechanics does not incorporate relativity. Rather, it is accomplished through the use of quantum field theory. We nevertheless arrive to the conclusion that the speed of causality is safeguarded, despite the fact that this reduced picture is presented to us when two hypotheses that are drastically different from one another, both of which are supported by an overwhelming amount of observational evidence, arrive to the same result in a wholly independent manner. There is a sensation that we are catching a glimpse of some more profound truth here, that these are not merely books of each theory or oddities, but rather a characteristic of the cosmos itself is essential to understand. In spite of everything that has happened, the story is not yet over. In the field of theoretical physics, researchers continue to look for ever more in-depth explanations of how the universe functions. It seems certain that one day we will find a more in-depth model that naturally unites everything that we have learned up until this point, and perhaps even some new truths as well. It is almost as if one is hoping for a miracle to discover whether or not those new truths would provide the key to fast-forward travel. You are free to go ahead and wish for it to be true, but none of us can assert that it is essential or even likely to occur. It is possible that one of the aspects of maturing as a technological species is coming to terms with the fact that the cosmos seems to be committed, even dedicated, to ensuring that slow speeds are maintained over its territory. Please believe me when I say that I'm aware that this is not the response that either you or I were looking for. In contrast, praying for a miracle such as winning the lottery, or expecting that your difficulties will miraculously disappear one day, does not serve as a fruitful approach to creating future growth. This is true just as it is with our own life. When you reach a specific point in your life, you only have to accept the hand that you have been dealt and make an effort to make the most of it. Frequently, the outcomes that can result from this are significantly more fantastic than you had anticipated initially. As a result, I do not believe in miracles. Nevertheless, I do believe that we have the potential to make the most of the situations that we find ourselves in. In conclusion, until we meet again, remember to be mindful and inquiring.